So, chapter 16, we're going to look at entropy. In fact, what we're going to be doing is continuing on our discussion of thermochemistry. Now, we know thermo being heat, chemistry, obviously the heat that is into chemistry or involved in chemistry. And what we're going to try to do in this chapter is figure out whether or not a reaction should be spontaneous, whether or not it will actually occur, and if it does occur, how much useful energy can we get out of it? So in this chapter, we're going to ask ourselves, what is a spontaneous reaction? What does that mean? We're going to talk about entropy, measure of disorder. We're going to talk about free energy, which is the maximum amount of work that you can get from a reaction. We're going to discuss the relationship between entropy and free energy and the second law of thermodynamics, as well as thermodynamics and equilibrium. So my first advice would be to go back to chapter 5 and review thermodynamics. In particular, I need you to remember what enthalpy is. Enthalpy we designate as a delta H. We remember that enthalpy is heat at constant pressure. And if we have heat here at constant pressure, and remember our delta is our change, and we've got a couple of terms, remember that we consider delta H not sub F, where F here was formation, which means to make it from its elements. And we remember that delta H here of a reaction, it's going to be the sum times the number of moles of the delta H naughts of formation of the products minus the sum times the number of moles times the delta H naught of formation of the reactants. All right, so we use those, and we're going to use delta H to consider thermodynamics in this chapter, chapter 16. Spontaneous. Spontaneous means that a reaction is going to occur without outside intervention. Please note, this is not kinetics. And when we say without outside intervention, what we are not discussing is activation energy. So even though we know, for example, combustion requires the addition of a bit of a flame or a match, something to take and drive the reaction over the activation energy, we have to go over E sub A. That is not what we're looking at when we're thinking about spontaneous. What we need to imagine is after you have put in the match, if the reaction continues to proceed spontaneously. Otherwise, it would be a reaction that you would continue to have energy to, add energy to, or do work to, and that would be a non-spontaneous process. We're not talking about how fast or how slow. It could be either. And this, again, is not kinetic, so it's just going to tell us if a reaction will occur, but not how fast the reaction will occur. So if I have a gas and the gas is separated between two containers, and I open up the valve in between these two containers, the gas will spontaneously diffuse onto the other side. That is a spontaneous process. Now, non-spontaneous would be suddenly all of the atoms on this side going over and joining the other ones and going back to the area where all of the gas molecules are on one side. That would be non-spontaneous. In order to get all of these gas molecules moved, we'd have to add work. This happens by itself. By itself is going to be spontaneous. So we are going to define entropy. Entropy we symbolize as a capital S, and entropy by definition is the number of ways to arrange the system. So we're going to look at the number of ways to arrange the system or whatever it is that we are studying. The more ways that we can arrange it, the higher the entropy. Entropy is a measure of disorder. The more disordered something is, the higher the entropy is. So some things are inherently more disordered. Gases are always more disordered than the corresponding liquid, which is going to be more disordered than the corresponding solid. Why? Because it's got more ways that it can be rearranged or moved, or it has more possible energy states. When you go from a solid to a liquid to a gas, your process is inherently going to go from a lower entropy to a higher entropy, which means it's going to go from something that is more ordered to something that is more disordered. So, entropy is a measure of the number of ways a system can be arranged. A very ordered system has very few ways it can be arranged in a low entropy. A crystalline solid is defined to have an entropy of 0 at absolute 0 because it is so incredibly highly ordered. By the way, that is the third law of thermodynamics. Entropies are tabulated. We call them standard entropies. Standard here is this little 0 that we have, and standard simply means pure substance or pure stuff, whatever it might be, at 1 atm or 1 molar. And these are tabulated as a function of temperature. So there's no temperature implied. So temperature standard does not mean any particular temperature, which is why when you look at your tables, they always state the temperature. So most of these we're going to find are standard entropies at 298 kelvins. This is in a appendix at the back of your text. So ways of arranging things. This is disordered. Imagine taking away the little separations and it'd be really disordered. This is ordered. The fewer ways that you can arrange it, the more structure it has, the lower the entropy and the smaller the value of S. Entropies are tabulated. Note, they will be tabulated at a specific temperature. Here, this is 298 Kelvin. And when you need a value for an entropy, and by the way, these are molar entropies, they are going to have units of joules per mole Kelvin. The Kelvin is very relevant because as the temperature of anything goes up, its entropy is going to go up because the particles are moving more, which inherently gives them more disordered. Otherwise, these are going to be tabulated at 298 Kelvin unless you find a different chart. If we want to compare particular compounds, we can consider carbon as a solid in two forms. We either have diamond, which is a very regularly ordered shape, or graphite. Graphite comes in sheets because inherently if you have a sheet, you can take and flip the sheet over or change the direction of the sheet. The graphite here is going to be more disordered than diamond, so the entropy of graphite is going to be greater than the entropy of diamond because graphite is less ordered or more disordered. In general, the larger or more complex a molecule is, the higher the entropy. The hotter a substance gets, the higher the entropy. And if you take a solid and you dissolve it in water, so for example, if you take NaCl as a solid and you use water as the medium, and you dissolve to make the ions that are now going to be floating around randomly in this water, inherently this is ordered in a crystalline solid, and this is going to be messy or disordered. And so a dissolved solid is going to have a higher entropy than the crystal. So we can look at the change in entropy. If when we go from reactants to products, and the disorder increases, so let's say that our products are more disordered and have a greater entropy than the reactants, and these would have a lower entropy, just for example. If this is the case, then our delta S for this reaction is going to be positive. If we go from, in this case down here, if we go from disordered, so why is this disordered? Because it has a gas molecule in it, to more ordered, more regular into this crystalline solid, the S here is greater than the S of the products, and the delta S, the change in the entropy for this reaction, will have a negative value. So if we go from a solid into a solid plus a gas, we know that this is in a sense falling apart. It's got more options. It's less constrained. Therefore, the delta S for this reaction is going to be positive. this side is going to have a greater entropy for the products are going to have a greater entropy than the reactants. So what if we took sodium as a solid with some chlorine as a gas and make solid sodium chloride? Well, the key here is to look at the number of pieces as well as the states. Because this is a gas, gases are inherently disordered, and these are both solids. It's going from more irregular to regular, and the delta S is going to be negative. If we go from a solid to a liquid, our liquid is less constrained. It's got more motion than the solid does, and the delta S for this reaction will be positive. So what if we look at these guys? Well, if we take water vapor and condense it, so we take H2O as a gas and turn it into H2O as a liquid. If we look at the states, we know that a gas is more disordered than a liquid. Therefore, the change in entropy will be negative. If we get sucrose crystals from a supersaturated solution, well, this means that we are going to take a solution of sucrose, aqueous, and turn it into sucrose as a solid or crystalline. Anything dissolved in water is going to be more disordered than a crystalline solid of the same version. Therefore, our change in entropy or disorder will be negative. If we heat a gas up, anytime the temperature goes up, the entropy goes up. So the change in entropy for this process will be positive. If we sublime dry ice, meaning we take carbon dioxide as a solid and go into carbon dioxide as a gas, the solid is more ordered than the gas, so the change in entropy for the process is positive. Now, we can actually calculate a change in entropy from a reaction from the molar entropies. And this would be the standard molar entropy. The units here are off. These really should be joules per k mole. But with that in mind, we can calculate this. So if we have a reaction where we're going from 2 methanols and 3 oxygens as a gas into 2 carbon dioxides and 4 waters as a liquid, we can get the change in entropy. The change in entropy, the equation is going to be the change in entropy for a reaction. It's going to be the sum, so we're going to add up the number of moles of the entropies of products minus the sum times the number of moles of the entropies of the reactants. So we're going to consistently do products minus reactants. Again, why? Because our delta is going to be final minus initial. So we're going to have 4 moles of water multiplied by 70 joules per mole K plus, ignore that right there, plus 2 moles of carbon dioxide multiplied by 213 joules per mole K minus our methanol, so 2 moles of methanol times 126.8 joules per mole K added to 3 moles of oxygen multiplied by 205 joules per mole K. If we combine those terms, again, 2 moles of CO2 plus 4 moles of water minus, and here this negative has been factored through, so be careful here on the signs. Either subtract the entire amount or subtract both through these. I tend to do it like this. And when we do this, we're going to get a change in entropy of minus 361 joules per Kelvin. The moles are going to cancel, and this reaction is not spontaneous. All right, which leads us into another law. Our next law here is the second law of thermodynamics. And the second law of thermodynamics says that for a spontaneous process, there will be an increase in the entropy of the universe. All right, what does that mean? It says that delta S for the universe is going to equal delta S of the system. By the way, that is what we just calculated. and it's from the charts. So from the standard molar entropies on the charts, plus the change in entropy for everything else, which will be the surroundings. Note here that our universe is going to be made up of whatever our system is plus what our surroundings are. Now the system is easy. The system we simply get from the molar entropies on our charts. The surroundings are going to require a little bit more work.